Hey guys, welcome back to this episode of Question of the Week. I know it's been a little bit longer than a week, but we've all been busy with midterms. So we're back after a short hiatus. I'm Jason Wang. I'm joined by my friend Jarod Saxberg here. And today we're going to be talking about trees, which are a data structure you'll commonly find in a lot of these interviews. So this question that we're tackling is not super complicated, but I think it goes over a lot of the structure of trees and kind of how they work. So that being said, I'm going to be, again, writing the code here. And Jarod, the interviewer, can you go ahead and read the prompt for me?
Yeah, so the idea of this question is, given a tree, we want to find if that tree is a subtree of another tree. So again, in this problem, we're given two non-empty binary trees. So you don't have to worry about what happens if there's an empty tree. Is that a subtree? No, in this case, they're all non-empty. And we need to check whether tree T has exactly the same structure and node values of a subtree of S. So a subtree of S is a tree that consists of a node in S and all the node's descendants. The tree S could also be considered a subtree of itself. So we're given two example trees here. The first one, you can see the long form of the tree, and we're given 412 as a subtree. And by looking at these by visual comparison, we can see that is a subtree. So in this case, we should return true. But in example 2, we have the extra 0 appended to the bottom. So in that case, it's not a subtree. So that's kind of the problem. It's kind of a good introduction to binary trees and how to traverse them and work with them.
Okay, great. So a couple of things I want to point out here is I know a lot of trees that you get that are binary trees often are binary search trees. And for those of you that don't know, binary search trees are sorted. So in a binary search tree, the parent node is going to be greater than the child node on the left, but less than the child node on the right. But as you can see here, that's clearly not the case. These are binary trees. So all that means is you have a node with a maximum of 2 children, and they could be of any value. Okay. So the reason that's important is because initially I was thinking about if they're binary search trees, right? Like essentially I could just traverse them and just find it for the same elements, because if it's sorted, it would be roughly the same structure. But because they're binary trees, they're not sorted, but we can actually still kind of follow the same logic, right? Because as Jarod said, they need to match the same structure and node values. So 412 here in this example 1 matches this, and 421 would be no juju, would be no dice, right? Be a return false. Okay. So I guess my initial thought here is we already know what our subtree is going to look like. And we know that if it's going to return true, it's going to be found somewhere in there. So why don't we start off by just writing a super basic helper function that compares 2 trees and returns if they're equal, right? Because this tree is a class, a structure that we're kind of creating with this class here, there's no built-in equals function. So we have to kind of find a way to compare them. So let's just do public boolean equals, and we're obviously going to give a 2 tree node. We can just call it S and T, honestly. Okay, so the obvious case is, I would say, like if S and T are both null. Oh, geez. If they're both null, this would be return true, right?
Yeah.
Okay.
Yep.
So if they're not both null, but one of them is null, then we know that's going to be unequal, right? Because one of them is null, the other one isn't. So we can actually use an or here. The reason we can use an or here is because the only way it would get passed from this case to this case is if, they're not both null. If one of them is null and the other one isn't, normally you'd write, like, another way to do this would be to write 2 separate if statements where it's like if S is equal to null and T is not equal to null, and then have another else like F is not equal to null and T is, we can combine it with an or statement here. So the only time it would not satisfy this but satisfy this is if only one of them are null. So if one of them is null, the other one isn't, they cannot physically be equal. So we're just going to return false there. So the next thing we have to do is kind of compare their values. So kind of just writing some pseudocode here. We know that the value of the first node has to be equal, right? So I'm just gonna so we have to know. Sorry, s dot val. I don't want to put x there. S dot val is equal to. We have to know that that has to be true, right? Yep. What else? Okay, the way that trees work, there's a lot of recursion going on, right? Because it's kind of like a linked list in that the left and right references are other tree nodes. So we can actually recursively call equals here. So we know that like equals s dot left, t dot left, that has to be true, right? Because all the descendants have to be true. So we know that this has to return true somehow. And finally, we know that the same thing with the right. So
what kind of traversal is this? What order is this?
So in the order that it's written, I actually don't know. Jared, do you know what order of traversal this is?
Yeah, so this is pre-order traversal, because in pre-order traversal, we want to look at the root node first, and then we want to look at left, and then we want to look at right. There are three different types of traversal, because there's three things to look at in a tree. You have in order, which is like left, root, then right. Pre-order, which we're doing now, which is root, left, and right. And then there's also post-order, which is, I think it's left, right, and then root.
Yeah. So if you kind of think about what those words mean, like in order is like pretty straightforward, right? Because we as humans read from left to right. So you're kind of going like left, root, right. Pre-order is you're kind of reading like the top down, and then post-order is the opposite of pre-order. So you're reading down, top, bottom up. I don't know. But that's like a pretty easy way to remember those. But thanks for pointing that out, Jared. That being said, so we need to know that these all combine to true. So what you can do here is we can write an if statement that says if all these conditions are true, then return true. Or, if you want to be one of those like super cool guys that doesn't do that and directly jumps to a return statement, you can just do this, right? So this might look kind of ugly, but you can return. So we need s.val and t.val to equal, right? We also need their lefts to equal. So we can combine this with an and statement and then do it again here. So this is pretty much only going to return true if all of these functions are satisfied, which we have is like this kind of long and statement. And again, you could switch this into an if, kind of like we did here. If all of these are satisfied, then return true. Or you can just do like this. The reason I'm doing like this is kind of show you a bit of variation. Now you can kind of shake up your returns, but it all kind of results in the same thing. So now that we have this, we have an equals function. So now we know whether or not to compare two trees. Okay, cool. So what's next? Because we're not just comparing S and T, right? Because which one is a subnode?
T is a subtree of S.
Okay, so T is a subtree of S. Okay, so like T and S may not be equal, but T just has to equal to some part of S. So we're going to have to do some traversing here, right? So there are a couple ways to do it. I mean, Jared just gave us 3 ways, like conceptually, right? Post-order, pre-order, and in-order. But writing is a little bit more difficult because you can't just kind of, like, we have to figure out what we want to return. So why don't we, let's do this. Let's write. So we have a function called traverse, and we'll give it the same inputs here. So what I want to do here, I want to figure out a way to travel between these two trees. Jared, do you have any ideas?
So let's think recursive here. Think about how we're doing this equal statement here. Just check if things are equal. We're going to be recurring through stuff. So let's kind of keep on that same idea.
Okay. Okay, so you talked about it's very similar to equals, and you talked about recursion. Oh, okay. So we know that traverse, pretty much what it's doing is like it's kind of traveling through both nodes. Like it's given, again, these S and T, it's assuming it's the root of some tree, right? If you pass it tree S, it's going to start from 3, and right, if you pass it tree T, it's going to start from 4. But again, because S.left is a tree node object, we can pass traverse dot like s dot left, and it'll start at 4, and then it'll kind of go through here. Okay, so how do we do that? Okay, well first, well, we have to know s is not null, right? So because s is the master tree, right? I keep forgetting this. This is like that.
Yeah, S is the master.
Okay, so s can't be null. If s is null, then we're toasted, right? Because it's like, what are you gonna get, right? Okay, and then what other conditions do we have to check? So there's 2 ways this can work out. If s and t are already equal, then we're good. Then like we pretty much like return the function here. So like but we want that's like one possibility. So I'm gonna encase this in a bunch of ors because I think there are actually a couple ways for this to work out for us. So if s and t are equal, which we can check with our nifty helper function here, s and t equals, or what's another thing? Okay, if they're not equal, then we're gonna check both the left and the right tree because this subtree t could be a left or a right. It could be like on either side. So why don't we recursively call, based on what Jarod told us, traverse s dot left and t, because we need to keep t constant, right? Because we're always looking for that subtree. We can iterate through the tree that's our master tree, which is s, right? Or why don't we traverse s dot right? Okay, cool. So pretty much this will keep recurring down up until you get to a leaf node and there's no more left or rights, in which case, do we handle that case? Yeah, in which case like s will eventually be null because we'll pass it s dot left at a root and it'll be null, and this will not satisfy, and because it's an and statement, the whole thing will kind of terminate.
Yeah, so let's try walking through this with example 1, because I know some people really could struggle with recursion. Actually, let's finish writing out that is subtree, because I think this is pretty easy function, but let's make sure we go through this, really kind of like break it down for people, because recursion can be kind of tricky, and it's kind of helpful to actually look at it, and that way we can test if it's working.
Yeah, okay, cool. So again, what the traverse function does here is it pretty much, given 2 nodes, it'll go through the whole thing and find a subtree of s that will equal t. So this is actually our function. Okay. Return to Boolean. So we could either change this to be is subtree, or we can just call it here. So we could just return traverse s and t, right?
Yeah, I think it's a little bit clean that way too, right?
Okay.
Using a little bit of helper functions.
Yeah. So one thing I will say is, personally, I found with recursion, like if you have helper functions, it kind of helps you think of it more incrementally. Because if you are doing recursion, you're throwing a lot of it together, your like mental recursive stack will get super confusing. So like notice, I mean, we could have honestly theoretically done all of this in one function, but this helps us kind of separate and compartmentalize mentally what we have to do at each step. Right. So as Jarod said, actually, let's do a high-level overview, and then I'll demonstrate this on example 1 step by step. So the high-level overview, we call is subtree on a big tree S and a smaller tree T, and we want to find is T a subtree of S, and what that means is, can we find the tree T within S somewhere, right? And the only line for that function is traverse with those same 2 inputs. So we jump down to our traverse function. Our traverse function pretty much just says, if the master tree through which you are searching is null, right, then it's going to return false. That's impossible, right? So we have to check the master tree is not null, number 1. And then number 2, does it satisfy one of 3 conditions? Do S and T equal, at which point T is obviously a subtree of S, because any tree is a subtree of itself, which I think they say, right? Tree S could also be considered as a subtree of itself, so I know that. And okay, that's one condition. The other condition is it has to pass traverse s dot left or s dot right with t. So pretty much just saying, if they're not equal, well, is t equal to the tree on the left, or is t equal to the tree on the right? And this will keep going down until they find the match. And then the only thing we have to go over again is equals, which I think is actually the most straightforward part of this code, which is just checking, are the 2 trees null? If so, true. They are equal because two null trees are equal. If only one of them is null, then obviously they're not equal. Otherwise, again, recursive call here, return true only if both their values are equal and both the left trees are equal and both the right trees are equal, right? So if there are two non-null trees, you're gonna have to satisfy this condition. But the way that it recurs, again, with trees, you'll always go down to your leaves pretty much as your base cases. And then in that case, like you'll eventually get to a null and you'll return true and that'll get passed up.
Yep.
Cool. Jarod, are we ready to dive into example 1 here?
Yeah, I think your algorithm right now sounds really, really good. So let's try working with it on example 1 and kind of get a high level look. A high level look with this example.
Okay. So we get 3, 4, 5. We get these two trees. So let's pass those to traverse. So is tree S, which is this tree, null? It is not. So we're good to go on that one. And now we check these 3 conditions. Are S and T equal? Well, no, just don't even pass the eye test, right? Well, traverse S dot left and T. Okay, so let's pass 4, 1, 2 through traverse. So 4, 1, 2, this tree right here is our new S, and this is still our same T. Okay, is S null? It is not. It has some elements. Are S and T equal? 4, 1, 2. Okay, let's pass that to the equals function, right? Where we have the tree 4, 1, 2 is our S and 4, 1, 2 is our T. Are they both null? They're not both null, so we don't pass this. Is one of them null? No, so it doesn't pass this, right? And then are the values equal? So is 4 equal? Are the root values equal? Yes, they are. And then are their left and right subtrees equal? So in this case, we're comparing 1 and 1, 2 and 2. Okay, so they're equal. So this will pass all the way back up on this case true, which means that this whole thing will evaluate to true, which gets passed back to return traverse, which should return true. So in that case, unless I missed anything, it should work for example 1. Does that make sense?
Yeah, I think that sounds pretty good.
Okay, cool. So if we look at example 2, it's pretty much the same thing. So we already know we're going to skip the first step, right? We already know we're going to have to dive into traverse S.left T. So in this case, S.left T is 4, 1, 2, 0, and that's our S, right? And then this is the T. So S is not null. Cool. Are they equal? No. Traverse left. Okay, so the left of this S is just going to be 1. That we already know. We can kind of like, do you want to go through that example? 1 is not equal to 4, 1, 2, right? This single node is not equal to these 3. So then it's going to go to S dot right, which is going to be 4, 2, or it's going to be 2, 0, which again doesn't satisfy. It's not equal to T, and it will never be equal to T. We can catch this because usually when we're performing the equals, when we're comparing 4, 1, 2 to 4, 1, 2, right? Like S dot right is just the node 2. T dot right is just the node 2. In this case, in example 2, S dot right is 2 with the left child of 0, which is not equal to just node 2. That's why it doesn't pass false, right? So even though, again, it's technically those same elements in that same order is arranged, think of this as a node with the same value, but an additional reference, right? Even though they have the same value, those trees are not the same because this node is referencing another child, whereas this does not. This node has kids. This one does not have kids. So they cannot be equal, which is why this case would return false. Cool.
Yeah, it seems pretty good.
Jarod, should I run my code? I'm very nervous.
Yeah, let's run it before we submit it. Let's just see if it passes one of these straightforward cases, and let's see if it compiles and everything.
Okay, I'm stretching. I'm ready. Also, look, LeetCode just makes me nervous when I run my code. I was talking to Jarod about this before, but okay. Okay.
Okay, great. True.
So this case is the same as this case, by the way, right? 3, 4, 5, 1, 2, 4, 1, 2. Cool. Okay, now this is the big moment.
Let's see.
Oh,
Success.
Okay.
That memory usage, though.
So we live in a capitalist society. We can have as much memory as we want. That's fine.
True.
Money cannot buy you time, though. So our time is pretty spicy, faster than most people. This is like an A+, right? So let's kind of talk about why that is. Because realistically, like, we're going to visit each subtree at most once. We're never doing any sort of redundant operations, right? So it should be O of n. And remember, trees are a little bit different. Where like O of n, where n is the number of nodes, because each node again is technically a subtree. So you have to visit each one to confirm, because you're not going to pass up false until you hit a null. So worst case scenario, like if we go to the description, worst case scenario, we're looking for the node 5, right? Let's say you check 3, 4, 1, 2, and then 5. Like the worst case is you'll have to check every node, right? So it grows linearly as a function of like how many nodes there are in the tree. In terms of space, Jarod, why is our space so bad? Can you tell me more about why it's so bad?
In that case, this is just a feature of LeetCode. Like, memory usage is very hard to judge, I guess, virtually through a computer system. So like you could, if you run this again, I guarantee you could have a different number for your memory usage. And that like 38.8 could go to like 38.7. And now all of a sudden you're like in the top 90%.
Yeah.
See, now you just went to 38.9. So you just went up a little bit. So it's very hard to like judge that. However, it's still pretty consistent. Like if you were to do something where you're allocating a list in here, that memory is going to go up. So memory in this case, your solution isn't, you're not allocating any memory on your like right away. It's not obvious what you're allocating. The stuff that you're allocating is the recursive memory. So you're building a stack that the stack is going to grow with every recursive call. So the number of recursive calls you make is going to increase the size of your stack. So you could say that recursive call could be n, and that n would be how deep your tree is. So every level on your tree is going to call a new recursive. It's going to create new recursion.
Right. So think about it as if we had
your stack.
Yeah, think about it if we had a tree with like 4 left trees to check, right? And we call traverse on the s.left, which leads to this one, which is this one, which is this one. These don't disappear. They're like waiting for the results of the base case, right? That's how recursion works. Like it goes all the way down into the base case and then returns that value all the way up. So whenever you use recursion, like one of the main downsides of recursion is like the space. Your recursive stack will get pretty big. So that's something to pay attention to here. But overall, I think this is a pretty nifty solution. Jarod, let's say you had to come up with another solution. Now we don't have to write this code out by any means, but like, what would be like another way that you could see solving this problem?
So actually, I worked on this problem once before in a mock technical interview. It's what we do here. So kind of a sellout for that. But in my solution, I wasn't really confident with recursion in this sense, where I was seeing trees equal each other. The way that I saw this at first was, okay, well, what if we just traverse S, turn it into a string? What if we traverse T, turn it into a string, and then see if the substring created by T is a part of the string that was created by S. If that substring exists, then we return true because we found it. If not, then we return false. So the way I did it was a little different, just working with strings. So depends really on how you think. I think this recursive solution, it's much better in time, because in the solution that I thought of, you have to traverse both of these trees at least once, where with the recursive one, you can end early if you find the solution early. But in the solution that I made, you have to at least go through every single node in every tree. There's no ending early in that case.
Yeah. So kind of just to visualize Jared's example here, right? Like if we were going through S, and you can really pick any traversal method, but it has to be consistent with both S and T. So let's say we're doing, do you want to do in order? In order makes sense here, right? Like if we go left root right, so it'd be, you go left all the way down here to 1.
That'd be fine.
What's up?
That'd be fine, yeah.
Okay. So if we did left root right, we'd have like 1, 4, 2, 3, 5, right? Because you go all the way left to the root and you do the right, but this is all the left of the master tree. So then this would be the root. So then you have 3, and then you have 5, which gets added on last, right? And then if you do that,
one thing though that you're kind of doing here that even I kind of messed up on when I did it is you need to account for the nulls, because nulls in this case, you have to make sure the structure is the same. So you could have this where you have 1, 4, 2, 3, 5, but then what happens if you have a tree? So in this case, we're doing this post order. What happens if we have a tree that's like a root of 2, the next node to the left is 4, and then the next node to the left is 1. Then we would be 1, 4, 2. But that's not a subtree because it's not a valid structure. So we need to include the sense of nulls in here.
Yeah.
So
and
like,
we can actually demonstrate that with. Oh, sorry. Go ahead.
Yeah. So in that case, this tree really. So wherever we have like our 1, 2, and 5 here, since these have no children, what that basically means is they do have children, but they're 2 null objects. So it'd be like you'd see 3, 4, 1, null, null, 2, null, null, 5, null, null. So in this case, you need to, if we're building a string, we could do, depending on the traversal method we do, in this case, we're doing 1, 4, 2. So we would be null, 1, null, 4, null, 2, null, 3, 5, or 3, null, 5, null. So this is kind of a kind of weird way to do the order. I think it'd be better in this case just to do pre-order like we're doing already with the solution. So we would have, sorry, I lost my train of thought here.
No, I think we get what you're saying, right?
Yeah.
Yeah, because what Jarod is pointing out is like, if you don't account for the nulls, what you might end up mixing up is something like example 2, where you see something like, oh, at one point you get 1, 4, 2, and it will be a substring, but if there's a 0 after that 2, whereas there should be a null, you might return true when you shouldn't actually, because the structure isn't matching. Because although the same nodes are there, they're kind of embedded within a greater subtree, and so that actually doesn't count, right? Because again, 1, 4, 2, 0, this whole subtree, it looks like this is a piece of that, but the 0 kind of makes it not that way. And if you have a substring method, if you don't account for the nulls, normally how you would check for substring, this would probably return true. So what Jarod is saying is like you need to make sure to include nulls if they are leaf nodes, regardless, if you're going to do that approach.
Yeah, and also depending on how it's set up, like in this case, we don't know, like we could have digits in here that are up to like multiple digits. So it's also good practice to put a space in between them. So we could have like 1 space n space n space 2, something like that. Because if we had, say we have like 22 in a data, like in a value, and then we had a tree that's 2, 2, it could potentially return true there as well. So we need to include a space in our string to make sure that we account for that.
Yeah, or some sort of character that separates like numbers from just like single spaces, right?
Yeah.
Cool. That being said, so this is, yeah, it's nothing too complicated. The ask is pretty straightforward, right? But this kind of shows you how trees work. So trees, you have a root node, and then I guess a binary tree, you have a root node, and then you have 2 children, which are also tree nodes. Any node that's at the bottom, any node with no children we consider to be leaves. And as you can clearly see, recursion is a pretty common way to solve a lot of problems with trees because, again, you can call it on the root and then call it on the left and the right. So that's the question of the week this week. We'll probably be doing more tree questions as they come up. We'll probably do a medium next time. If Jarod and I are, we're kind of shaking off the rust here, but, we're going to try and diversify the number of data structures that we talk about. Because I know first couple episodes were just general coding questions, but I think we want to start diving into the fundamentals of the pieces in your toolkit that you would use to solve a lot of these different problems. So join us next week where we'll be tackling a new and fun, exciting problem. Peace out, guys.